if you study a little bit of math, you might have come across a sort of popular debate on whether or not 0.999 repeating endlessly is equal to 1. And this is obviously a very mathematical question, and so today we're going to use math to tackle the answer. And the first thing we're going to do is we're going to rephrase this question just a little bit. Realize that if we have two numbers, let's call this one A, and let's call this one B, that if A and B are equal, then we can pull the strategy of subtracting B from both sides to get that A minus B is equal to 0. So the question we're going to be answering, which is really the same question that we asked at the beginning, is does 1 minus 0.999 repeating equal 0? And if not, what does it equal? What is the difference between them? How much smaller is this than 1, if at all? And the messy term, right, the thing that messes people up about this is the fact that this number looks like it's just ever so slightly smaller than 1, right? But at the same time, how much smaller is it really than 1, right? These 9s just, they don't stop. We've got a 9 in the 10th place. We've got a 9 in the 100th place, a 9 in the 1000th place. And that makes it a little tricky, which is why there's a debate at all. And one way that mathematicians like to tackle things, when you have to deal with something that has an infinite number of terms in it, or in this case, a number whose decimal representation goes on infinitely, is let's look at what happens in a finite case. Let's look at what happens when there are only some 9s, when maybe there are only 3 9s. What if it's 1 minus 0.999? Well, that's an easy one. We know that we've subtracted away. We can treat this as just 1.000 minus 0.999, right? And from this, we get that the answer is 0.001. Okay. And so they look at cases where it's finite. And then a mathematician might go out, okay, what happens if I include 4 9s? Right? Now I have 1.0000 minus 0.9999. And that just means we add on another 0 to the beginning of our number. Right? And mathematicians will do this, and they'll look at finite cases, and they'll go larger. We started with 3 9s, then we went to 4. Next we could go on to 5 and 6 and so on. And see if we can find some kind of pattern that develops. And the way that we're going to tackle what happens in the case where there are infinitely many 9s is we're going to see what happens to this pattern as the number of 9s grows infinitely large. Right? So let's do that. Let's go to the case of 5 9s. 1.00000 minus 0.99999. Well, you can just think of this as having this really large number minus this number of 9s, 0.00001. Right? And we do see a pattern forming on this side. Each time I add one more 9 over here, I have to add one more 0 over here. And so let's call this, let's say that having 3 9s, we're going to create our own little notation for this problem. Let's say that if I have 0.9, we're going to call that S1. And you'll see the pattern as I go on. Let's say I have 2 9s. Let's call this S2. Let's say I have 3 9s. We're going to call that S3. So the number in the subscript here after S is really telling us how many 9s am I writing after the decimal point, right? And ultimately, we want to see what happens when there are infinitely many 9s. And so let's call that S infinity. Okay? And let's look from the pattern that we just saw over there. We're going to start asking this kind of question. We're going to see what happens, right? 1 minus S1 is really just 1 minus 0.9. And that just gives us 0.1. 1 minus S2 is giving us 1 minus 0.99. And that's 0.01. Right? So on and so forth. So let's look at this. 1 minus S1 gives me a 1 in the tenths place for the difference between these two numbers. 1 minus S2 gives me a 1 in the hundredths place. 1 minus S3 gives me a 1 in the thousandths place, which happens to be the third place after the decimal. And so, what about a general case? Let's say I stop at some number n, right? N could be 1, 2, 3, it could be 500, it could be 10 million, right? It just says, look at the number of decimal places. The first, second, the third, 1, 2, 3. Go out all the way, right? Zeros all the way until you hit the nth place after the decimal. Then write that 1, right? So 1 minus Sn, which is a 0 with n nines after the decimal point, gives us this as the difference between 1 and Sn. And we see then that each time n goes up by 1, the value of our difference shrinks by a factor of 10. Right? It started as a tenth, then it went to 100th, then 1,000th, and it's going to keep going on like that as n grows by 1. So what's going to happen as n grows to infinity? In order to investigate what happens, right, we defined S infinity to be this. So we're really then asking, what is 1 minus S infinity? In the case where I'm saying, wait infinitely long. And then at the very end of that, write a 1 in the final decimal place. Now do you see how there's maybe a kind of issue with that? Wait infinitely long, write infinitely many zeros, and then write a 1? What could that mean? I'm never going to finish writing these zeros, so do I ever really write that 1? And let's think about that a little bit then, because what would the value of that 1 even be? We see that each time we go out 1 further in our series, the value of this 1 shrinks by a factor of 10. Right? So, letting it go out 3 times lets it shrink by a factor of 10 3 times, meaning it shrinks down to 1/1000th of 1, right? Letting it go out 100 means we've forced this number to shrink down by a factor of 10 100 times. Now we're saying, right, as when we want to find out what happens with S infinity, we're saying let n go to infinity. Let this number shrink down by a factor of 10 infinitely many times. Well, what happens to a number if it keeps shrinking by the same factor infinitely many times? Right? You can imagine taking a box. Let's let the area of this box be 1. Okay? 1. All right? For S1, we're saying cut out all of the area inside the box, except for 1/10 of it. Okay? So we're going to cut that out. Then we cut it down by a factor of 10 again. So take whatever's left and cut out 90% of that too. Then take what's left and cut out 90% of that. Then take what's left and cut out 90% of that. This remaining portion is shrinking, and it's shrinking really fast. And you can see what happens is that as we go out further and further, as we iterate further and further out, this area is shrinking down to 0. So we see then what this means. As n goes to infinity, as n goes to infinity, 1 minus Sn is shrinking down to 0. So this will only happen, this value will only be 0 if there are infinitely many 9s in Sn. But what is S infinity? We are saying that there are infinitely many 9s. And so the difference between this and 1 ultimately shrinks to 0 because there are infinitely many 9s, because we are cutting down the area that many times that the difference ultimately shrinks down to 0.